Okay, let's get started. Welcome to lecture 7. So what we'll do today is discuss the BCH code. So we introduced the BCH code last time. What we will see is we'll see more properties of the BCH code, analyze its rate and distance in more detail. BCH code. These are named after their discoverers. It was 2 sets of work. Bose and Ray Chaudhary is the first one. So it's Ray Chaudhary writes this as RHYCH, so I think they picked up the C from Ray Chaudhary and in independent work by, I don't know how to pronounce this. Oh. And so the code discovered by these two sets of papers named after them. And they're actually quite amazing codes. So let's recall from last time. So what did we have? We worked with a special case. We're going to take a special case of Reed-Solomon, Q to be F2 to the R. So it's a GF2 field, an extension of GF2. So take some for some integer R. We take the evaluation set yes to be F2R star to be the multiplicative group. So that in particular means n is equal to q minus 1 or 2r minus 1. And k last time we had set it to be arbitrary. We will still set it to be arbitrary, but I'll change the parameterization. K we call it n minus 2. So the whole code will be parameterized. So this is to ensure the parameterization. So n is 2 power r minus 1. That's the block length of the code. And there will be a parameter p. So just like Reed-Solomon were parameterized by k, k which was the degree parameter, here we parameterize with n minus 2p. And you'll see why t happens to be a more convenient parameterization than the degree parameter. And rather, this is not the original way BCH was discovered. BCH was discovered in a different fashion, and then they realized that it's actually the restriction of Reed-Solomon and stuff. Actually, they didn't realize it's the restriction of Reed-Solomon. They showed that so BCH was first discovered much before Reed-Solomon, and then they showed Reed-Solomon as sort of a generalization of BCH. The Reed-Solomon was discovered after BCH was discovered. But we will take this viewpoint. We think Reed-Solomon are more simple and more fundamental. We take Reed-Solomon code and look at BCH as the restriction of BCH code. So n, that's the parameter. So the BCH NT code, this code is just going to be the Reed-Solomon F2R, F2R star, those set of evaluation points. And the degree is now 2 power r minus 1 minus 2t. So that's the, so here, so we choose n to be of the form 2 power. So this is defined only for n being of the form 2 power 1. Intersection. So this is, so Reed-Solomon is the set of all evaluations of degree at most this polynomial, at most this over all the entire multiplicative group of the field. What we'll do is we will just take only those polynomials which evaluate to just 0, 1 on the entire multiplicative group. So in particular, I'm going to restrict myself to F2. So it's only with this intersection. So once again, so what is Reed-Solomon codes? Reed-Solomon codes are the evaluation of polynomials of this particular degree, 2 power r minus 1 minus 2, over this whole, over the multiplier. That's Reed-Solomon. Reed-Solomon, take every such polynomial, evaluate it. But I'm now going to intersect. I'm going to take a subset of this. Which subset I'm going to take? Some of these polynomials take values in the large field. There are 2 fields sitting here, F2. So think of this as this is always, there's a small field sitting, which is F2. There's a small field F2, there's a large field F2R, and F2, of course, think of it as 0, 1. There are two fields sitting, and these polynomials take value in the large field. That's how the polynomials are going to take value. But let's restrict our attention to only those polynomials which on every point in F2R star, that is for every point in F2R star, take only values in the base field.
So it's like a 0, 0, 0, 0.
So the code is just on the binary code. Because of this restriction, the alphabet now becomes the binary alphabet. Okay, it's just take this whole, take all the entire Reed-Solomon code word over this. You could get large symbols alphabet. Look at only those things in which every location you have only zeros and ones. It might be that there might be no such code. The all zeros is certainly one. If you take the all zeros polynomial, the constant zero polynomial, it is certainly a polynomial. The constant one polynomial is certainly one such polynomial. Question is, do there exist other polynomials other than this which have coefficients from the large field, but yet take values only all in the small field? It could be a very small subset. The first thing which we'll show is actually the heart of what today's thing is going to be. If T is small, this is actually a large set. This restriction is not really a super. It is certainly much smaller than the Reed-Solomon code, but yet we will show actually it's a large subset of this. That's what we will show. That's going to be the main, actually the first half an hour or so, that will be our main focus. The alphabet of the code word is binary. It's a boolean, it's over GF2. So for one, this is one for which we are constructing actually, it will be a code with great properties and it will be code over the boolean alphabet.
Q is not increasing. Alphabet size is not increasing.
Yeah, alphabet size is not increasing.
When you are making smaller T, you are removing two cells at once. What do you mean two cells? Like 2T is minor. So that this, if you change G, so this 2 to the power R minus 1 minus 2T,
yeah,
is the code length, right?
No, that's not the code. The code length is 2 power R. So this. One second. Let's write down what it is. That's not the code length. This is the parameters of the Reed-Solomon. Reed-Solomon notice for the Reed-Solomon. This is the field. This is the set of evaluation points. So that is the code length, and this is the an upper one, the degree plus 1. That's how we parameterize Reed-Solomon. That is the field, the set of evaluation points, and the degree parameter. Okay. But here will be the following.
You are restricting the polynomials of degree or degrees.
No. Where is all degrees less than that? Where is it only all
less than that?
The Reed-Solomon is always everything less than that. No. So when I talked about Reed-Solomon, you're looking at constant degree 1, degree 2, all the way up to this. You're taking all those polynomials, evaluating them on these points, and then you're asking which of these polynomials take values only in the base field. This is what we said last time. This is how we introduced BCH last time. The theorem which we are going to show is BCH in T is the, firstly, it's not hard to show it's a linear code because our Reed-Solomon is linear. If you inherit its linearity from this one, because if you add two such code words, it will continue to remain a BCH code word.
Add two code words, they are Reed-Solomon, we are adding them in F2 to the R, right? So
yeah, but so that F2 to the R is a superfield of F, is a super this one. So the addition will be the same addition which is happening over here. Yeah, so and you have to consider only scalar multiplication with Boolean. So that's fine. So that's why I'm going to put the square bracket. What's certain things we know, the block length is 2 power R minus 1. That's clear. The distance, it's going to be at least the distance of the Reed-Solomon code because it's only a subcode of the Reed-Solomon code. Therefore, it's going to have the distance. What we will just put is we just put 2t plus 1. So 2t plus 1 is the distance of the Reed-Solomon code, if you see. Okay, so it will have that. Now I need to put in over here what practically terms of. It shows at least so much 2 power r minus 1 minus t times r. And furthermore, it will be a cyclic code. Cyclic is just because the Reed-Solomon was cyclic over this set of evaluation points. Therefore, this will continue to inherit the cyclic code. Notice everything in this we have proven except, so we have proven the block length is trivial by definition. This is trivial by definition. This it inherits from Reed-Solomon. 2t plus 1 inherits from Reed-Solomon. Linearity is easy to check. Cyclic it inherits from Reed-Solomon. The only thing to show is this. Notice this is quite an amazing thing. Previously we only saw two code words, 0 and 1. Here I am claiming that there are 2 power r. So for like constant t being like 5 or 7, that's a lot of code words in the BCH code.
What is it? 2 power r minus 1 into t.
Huh?
2 power r minus 1
Minus 1 minus tr. Minus tr. Okay. Notice we did see a code which looks very much like this, the Hamming code, where t was 1. It was 2 power r minus 1, 2 power r minus 1 minus r, and 3. If you recall, the Hamming code was this. It's not surprising that the t equals 1 case of the BCH will actually be the Hamming code. And we'll see that. That is, it's not obvious from this definition at all, but we will show once we look at the BCH code closely, we will show. So the only that's the molecule. BCH inherits most of its properties from Reed-Solomon. Only thing left to argue is the dimension of the rate. Okay, that's the middle quantity. The 2 power r minus 1 minus tr is the only quantity we need to show. That's the only thing we need to show.
President is the constant distance constant.
Yeah, so let's get to that. So let's actually let me put this down and even before going to the theorem, let's stare at the theorem statement. Let's look at what's the size of the BCH code. So it's 2 power 2r minus 1 minus tr. Right? That's the size of the BCH code. The first quantity is 2 power r minus 1 is just 2 power n by 2 power tr. So n is 2 power r, so n is here 2 power r minus 1. So I can write this as 2 power n. So this 2 power r I can write as n plus 1 times t. So that's the BCH code, number of code words in the BCH code. What do we know about the Hamming bound? That any code, a code with say distance 2t plus 1 like the BCH code has, Hamming bound says 2t should be less than 2 power n times volume t n comma t. Because that's the Hamming bound. What is volume t n comma t? It is some number of the form 2 power n, some eta n per t for constant, for small t. In other words, the BCH code more or less meets the Hamming bound up to a constant in the number of code groups. If you take the logarithm, it really doesn't matter. So up to constants, the BCH code meets the Hamming bound. So Hamming gave a code just for b equals distance being 3. BCH is going to generalize it for 5, 7, all the odd, for several odd lengths. It's going to give a whole family of codes. It's not going to give exactly, it's not going to match the Hamming bound, but almost match the Hamming bound up to constant. It is BCH matches the Hamming bound. In that sense, it's a really remarkable code.
So, how is it Gilbert-Marshall bound or something?
No, it's weaker than the Gilbert-Marshall.
So it's somehow in the region when these two bounds are.
So notice okay, you're saying the Hamming bound is always worse than is always an upper bound over the hills.
Yes, I understand there is some gap between Gilbert-Marshall and Hamming bound.
But let's look at, I'm talking about small t. At small t, the distance of this code is, the fractional distance of the code is 2t plus 1 by 2 power r minus 1. So this is at delta equals 0.
Oh, okay.
No. So it's at this regime of the curve. It's at one of the, which extreme point is it? The top extreme? The top extreme point of the curve. So it's around that region. So it's not, it's where the Hamming, Gilbert, or all the bounds are sort of meeting. At that point, it is like, yeah.
Like already fixed it, there's a whole family of codes for a lot of n, but the distance is like fixed to it.
So this in fact answers why was BCH introduced? It was answers Hamming question. Hamming was able to handle one error and he gave a code of distance 3. Now you can ask the same question for Hamming with 2 errors. So you need a code with distance 5 to handle, you want to be able to recover from 2 errors. You needed a code with distance 5, and did we do? So BCH was the code that people discovered them, and it showed more or less it is tight. It's not as tight as a Hamming bound, which got the Hamming code exactly matches. You can't do any better than it. This shows it up to constant. This one, that was how BCH was first introduced. Of course, later on it was noticed that BCH actually has nice algebraic properties. It's actually the restriction of the Reed-Solomon code and stuff. The BCH, the way it was discovered was more to answer Hamming's question. Hamming answered this question for if the number of corruptions was 1. The number of you want to handle 3 corruptions, 2 corruptions, BCH is the answer to it. Okay. Any questions? Okay. So actually, a large part of the class is actually going to be trying to understand the dimension of the BCH code. So right now, they're asking this magical property. We are asking about polynomials over the large field. So there are going to be 2 fields always. This one, there's going to be the large field, which is GF2 to the R. And there's a small field GF2. We're asking polynomials with coefficients from the large field, which on all the non-zero points of the field evaluate to only values in the small field. Of course, there are 2 such polynomials, the all zeros and all ones. Notice that the polynomial, but we are asking are there several more polynomials, and what that theorem is actually saying is there are lots of such polynomials which actually do this. So the way we sort of try to understand this, we have all the tools except for one. We have almost all the tools to address this. Actually, we have all the tools to show 2r minus 1 minus 2tr. Instead of a tr, we have all the tools to show 2 times tr. That's also remarkably good. except that that will not match the Hamming bond. The Hamming will give you n plus 1 power 2t, which is quadratically off the Hamming bond, not constant off, it will be quadratically off. We'll actually do a little more work from 2t to get it to t, and then, okay. So how does one show that this is the case? Like, so if you're thinking of a code and you want to show this, what does that mean? You have to show that the code, if you can show that the code is defined by TR constraints. These constraints are not necessarily linearly independent, but if you can show the code has been defined by TR constraints, then certainly the dimension of the code is the global dimension minus TR, because each constraint can only reduce the size of the code. So what we'll try to see is show that our original description of BH, the orange one under the orange, actually that BH description can be expressed as something which has just 2R constraints, 2R GF2 constraints, linear constraints. Show that the stating that some string is in BCH will just impose some 2 TR constraints, possibly linearly independent. I don't know if they are linearly independent, but that doesn't matter because I'm only going a lower bound on the rate. Okay. So that's going to be our goal. We're going to find out a set of constraints that determine the BCH code.
So the example is not.
So actually, for small t, for t being less than log n, I think so, or some consequence log n, that is the rate. That is not greater than or equal to. That is the rate. That is the rate. That is the distance. That's exactly what the code is.
And for other things.
So other t, there will be dependencies that will keep in. You will see. In fact, we will exactly write down what are these TR constraints. Question is, are these TR constraints linearly dependent or linearly independent? If they are linearly independent, then that's the rate. If you see dependencies among them, this will depend on various values t, whether t, various number theoretic considerations will come, whether t n is, whether r is prime or not. All of them will begin coming in for large t. So in general, we'll need two things in our hand. So first thing which I want to talk about is we need to talk about things which are take values in the large field and small field, somehow going back and forth between the two fields. There's one very nice function which I do not know if you have seen, we call when you're working with extension fields with a base field and a larger field over it, called the trace function. And what we will do is a lot of this proof, it will be easier to state it in terms of trace is not necessary, but it will be easier to state it in terms of trace. So let me introduce you to the trace function. It's a useful tool to have. So the tools which we prove this will be, we'll have to use two tools. One is the trace function. And the other is the dual of Reed-Solomon F star K, where F is F2 to here. Notice we didn't study this last time. We studied Reed-Solomon F K. We studied the dual of a Reed-Solomon code when the set of evaluation was the entire field, not when the field was F star. So we'll do some more modification to understand that. But let's first go to the trace function. We have the trace function in general can be defined between any two finite extension fields, but here we'll just look at GF2 and GF2 to the R. These are the two fields we are looking at. So there is GF2, and which is some field of GF2 to the R, which is what we've been calling S. So the trace function map that goes from F2 to the R to F, and it does the following. It takes an element Z, maps it to Z plus Z square plus Z bar 4 all the way, Z bar 2R minus 2 plus Z bar 2R minus 1. It stops at Z bar 2R. Notice Z bar 2R will become Z again because you're working in F2 to the R. So this is the trace column. That's the trace column. The trace function is this map which takes Z to some of it. Of course, the reason way I stated it, it's completely unclear why Z is going into the base field. Z seems to be like a function from the large field to the large field itself. The way I done it. But let's take the square of this.
Wait, sorry. No, sorry. So this is going to GF2 is what the claim is.
Yeah. So let's just, how do you show something is in GF2? How do you show something is in a particular field of size Q? Just show that something satisfies x bar Q minus x equals 0. So let's take just the square of this. If you take the square of this, this is a nice place, the square will descend. So this will become z square, z bar 4, z bar 8. Each one of them will double. This will become z bar 2 bar r, which is z in this word. So you get back the same object. Therefore, this trace of z, so just
constant.
huh?
Cross terms are
No, we are working in GF2, therefore there are no cross terms. We are in this a plus b the whole square is a square plus b square word. So they are nice. So we are working in GF2. So it's important. So in general, if you have two fields, in general the field thing will be if you have fq to the r to fq, rather fp to the r to fp, it will be a z bar p plus z bar p square and so on, and that's what you will be doing.
So trace of z square equals trace of z, trace of z as 0.
Yeah, trace of
Z.
trace of z square is trace of z, but that doesn't mean what the next thing you said.
Trace of z whole square.
Trace
Trace of z whole square.
Yes.
Equals to trace of z.
Trace of z, yes. Yeah.
That means trace of z equals to
0 or 1. Yeah. So several observations we use. Yeah, that's the second observation which we're going to do. One is trace C is always in GF2. And that follows just from stating that trace Z whole square is trace. The second thing which I'm going to show is, of course, trace Z is linear. And that just follows from stating the same property. Trace of Z1 plus Z2 is trace Z1 plus trace Z2. That's just because a plus b the whole square is a square plus b square. So just apply, instead of z, put z1 plus z2. It just splits off as, this will split as z1 plus z2, that will split as z1 square plus z2 square, that will split z2 square. So trace is a linear map. So trace is a very nice linear map. So that's the second property of trace. Now, nowhere in this proof, so I want to say not just trace is a linear map, trace of alpha z is also linear for any alpha in the big field. The exact same observation. There's nothing, it will just multiply all of these numbers. So it will become trace of alpha z will become alpha z plus alpha square z square plus alpha power 4 z power 4, but it will still continue to be linear in the. So trace of alpha c is also linear. Okay. By the way, so trace z we said it's a trace z we said it goes to z GF2. Does it? It's actually non-trivial map, or does it actually go all the way to 0? Is it the all zeros function? Can it be the all zeros function?
There is the DP formula for this
Why is it not the all zeros function? Actually, I want to say you can just stare at what's written there and immediately say it cannot be the all zeros function.
Z when z equals to 1.
So what if R were even, that will go to 0. Trace of 1 will depends on certainly for R being even, trace of 1 is 0. For R being odd, trace of 1 is 1. Trace of z is if it has to be 0, it's a look at it, it's a polynomial of degree 2 power r minus 1. It cannot vanish on 2 power r points. It cannot vanish. It can vanish only on 2 power r minus. So it's a linear map. It's a linear map. Either it maps everything to 0 or it maps half the space to 0. And that says exactly it maps half the space to 0. It cannot have more than 2 power r minus 1 roots. It's a polynomial. Otherwise, this will become a polynomial which has to have z into 2 power r minus z as its factor. That it cannot have. Its degree is strictly lower. So trace z is non-zero. Not only is trace z non-zero, trace alpha z is also non-zero for exactly the same reasons. Trace for every alpha. So each one of them will be a trivial observation I'm making. So trace alpha z is the all zeros map if and only if alpha is a zero. Whenever alpha is non-zero, trace alpha c is some linear map from the large field to the small field, but it's a non-zero linear map. Okay. Okay, now that we have looked at all this, let us look at the set of all such functions. For every alpha, let's look at the set of all function of this type. Certainly, these functions are all contained in the set of linear functions from the large field to the small field. You agree? By definition, this is how I show. I show they are all linear functions. They are all actually what I say, they are actually also different functions. Trace alpha c can it be equal to trace beta c? The same reason. Trace alpha c equal to beta c, then alpha must be equal to beta. So these are all distinct linear functions over here. And how many linear functions have I produced over here? Okay, I'm going to, there's also the all zeros linear function. So 2 power r linear functions is what we have produced over here. How many linear functions are there from f2 to the r to f2?
2 power 2.
Huh? I want linear functions from f2 to the r to f2. 2 power r. Why? Once you send the basis elements, because it's linear, it's fixed. There are r basis elements. For each basis element, you have to decide whether to send the 0 or 1. There are 2 choices per basis element. There are r basis elements, therefore 2 per r choices. Therefore, this is equal to this. So we have shown one direction. We have shown inclusion by what is written above, and just counting dimensions, we have shown that they are equal. So this is actually, these two are the same set. What am I claiming? Any linear function from the large field to the small field, it has to be trace alpha z for some choice of alpha. They're all very, very simple observations. Why is this a useful notion? So suppose we had eta 1, eta 2, eta r were in the big field, and eta I, eta 1, eta 2, eta r were linearly independent. That is, these are elements in the big field, and there is no GF2 combination. What I mean by linearly independent, they are not they are F2 linearly independent. Of course, they are dependent over the large field, but they are F2. There is no binary linear combination of them that vanishes to 0. So they are they potentially form a basis for the large field. You can write every large field as some GF2 linear combination of these guys. Then I claim these functions. Look at these functions. Trace of eta 1z. These are now functions. Eta 2z. Trace of eta rz. These also have to be linearly independent. Because can there be any linear combination of them that vanishes to 0? If there's a linear combination, that means I can multiply this by b1, b2, bn, such that that linear combination is 0. Now trace linearity will say I can pull out trace, and this will say, so what on a,
we look at the
it's just the same thing. So it is also linearly independent. The proof is just similar. Suppose not. There exists b bar which is not equal to the all zeros vector, such that summation bi trace eta I z is the all zeros function. This is true if and only by linearity. This will be summation trace equals zeros function. That's true if and only if summation bi eta I is 0, which we know is cannot be true because the eta is chosen to be linearly independent. Therefore, these form, all I want to claim is these form a very, you take etas which are linearly independent, they form a nice basis for the entire set of linear functions. Why is this a useful? This one. So notice, underlying all of this, we've been using this isomorphism. This is how we built, if you guys know finite fields, we sort of use this isomorphism from F2R to F2R. I want to claim this actually gives you another, there are several such isomorphisms. There are several ways in which it all just says you can choose a particular basis and write F2R in this language. And I want to claim there's one very nice basis in which I take an element Z here and I map it to trace of eta 1Z, trace of eta 2Z, trace of eta RZ. So let's fix some eta 1, eta 2, eta R. We F2 linearly independent. Then there is this mapping. And this is a way of going from the large field to the small field. Notice one way we all obviously know every element in the large field. How did we get the large field? We took F2, adjoined it with X, took the ring of polynomials F2X, quotiented it out with an irreducible polynomial of degree R, and that's how we got it. So every element here is actually in one representation, it's a degree R minus, it's a polynomial of degree at most R minus 1. And so one such mapping was actually the coefficients of that polynomial. Every Z was a polynomial and one such mapping was the coefficients of that polynomial. Notice that's a linear mapping because you take two such, you take Z1, Z2, take two corresponding coefficients. So all I'm claiming is this part. So let's say, so you have Z you viewed it as some P of X, and Z1, Z2 was some Q of X. Then Z1 plus Z2 will be P plus Q of X. And furthermore, I want to say this linearity is not just maintained as polynomials, it's maintained as even at coefficient. The constant coefficient is, the constant coefficient here is, if you just look at this mapping from Z1 to the constant coefficient, that's a linear map from the large field to the small field. The degree, the S coefficient is also a linear map because of this property. Therefore, this mapping is actually a mapping from Z1 to, it is actually, it's one linear function Z, it's another linear function Z, and it's R linear functions. And these R linear functions are necessarily have to be independent linear functions. No linear function should be a function, should be a linear combination of this, and that I'm saying that's a candidate of the R linear functions. That's all I'm saying. There are multiple such candidates. For every choice of eta 1 to eta R, you have such, but this is a nice candidate. All of this is not needed for the proof that you said, but this is something just good to know. So that's why I'm doing it at this point of time. So that's all about trace. So any questions about trace? So trace was this simple function which we defined this way. That's the trace map. And it has all these properties. Right now, I'm stating all these properties only for GF2, but everything of this, there's nothing over here which is particular about the smaller field being GF2. It's true for any field, any finite field extension. I could have done the same, exactly the same operation. Questions? The base field could be GFQ, which need not be prime. It could be GFQ. That could be GFQ to the power R.
So, for example, if you want a map from GF2 to GF4, The base value would be what, say.
Z plus Z power 4 plus Z power, yeah, Z power 4 plus Z power 16 and so on. So the 2 will, that 2 is exactly the size of the base field.
From that to F.
GF2 to the R, and the base field not being GF2 but GF4.
But did we want the thing that we are sending it to be a subfield of this?
If 2 power R, if R is an even number, that will be the
Then
case. If R is an even number, that will be the case. Yeah. So much for trace. Now let's go back to the first two. And the second one is, second thing which I wanted to look at is the dual of RSF F star K. We had almost done this last time. We had the last time we had said RS F K. The dual of this is exactly RS F Q minus K. This is what we did last time, that is. And how did we prove this? We proved it using the following fact, using summation alpha power I in F star, alpha in F star is 0 for all 1 less than or equal to I less than we proved this identity and used this. Now, but actually while doing it, we had extended this map to also alpha being in F, not just F star. But this is the statement we proved, and then to prove that actual statement, we extended the summation to include alpha in F, included the 0 element also. Therefore, yeah. But here, right now, we don't want to include, because when you're talking about duality in F star, the summation will only go over alpha in F star. So let's try to find out what the dual of. So this statement, so let's just recall this fact. I'm going to write this in a slightly laborious fashion, same thing. So this also says alpha is an F star. For all alpha power I, alpha power j is 0. For all 0 less than or equal to I less than k. That's because alpha power I want to take the polynomials of this form, so I want this. But that summation I can't make I to be 1. So summation I has to be, this exponent I has to be non-zero. If it's 1, this is not true. If it's 0, this is not true. So for all I, this one, and for all 1 less than or equal to j less than or equal to q minus 1 minus k. We went by this, so the statement is true. It just follows from the previous statement, because if I choose I like this and j like this, I plus j will necessarily be greater than or equal to 1, and I plus j will be strictly less than q minus 1. But what does this mean? This means, so this q minus 1 is the same as n minus k, because we are working with the RS. Here n is equal to q minus 1, because we are working with the evaluation set being the multiplicative group. So what is that? That is for all f in RS f star k. What do we have? We have summation f alpha into alpha power j, alpha into f star is 0 for all 1 less than or equal to j less than n minus k. I was summing that. That was just for one monomial. I'm just summing it over all monomials. I get this. So this means that the alpha power j's are orthogonal to F alphas. For J being from 1 to n minus k, this is not the Reed-Solomon code. So all I'm claiming is this claims that the RS F star K dual is what? Is this object is summation over all Gi over x power I going from 1 to n minus k, where the Gi's are in this. It's take all these polynomials, evaluate them, but not take the polynomial evaluate there's no constant term. So those are the only difference between Reed-Solomon's duality over the whole field and the F star is the dual space here is all polynomials without the constant term. This is evaluated at only then I write this is the polynomial, but when I talk about the dual space, I have to evaluate it. So fair enough. This is not super nice, but let's work with it. For F star, the dual space is this. So last time I had said that actually for F star, the dual for any S, the dual space is always the right, is always Reed-Solomon. This doesn't seem to be Reed-Solomon the way I said it. In the problem set, we'll see a way to rectify this. We'll change the definition of what it means to be dual in order to make Reed-Solomon. So correctly, the dual space should have been going from 0 to n minus k minus 1. That will have been this one. That will not be dual under this definition of dual. We'll change the definition of dual in order to make that to be the dual. For every S, we can do that. That will be the problem set in this one. But for now, we'll use this. Okay. Okay. So why have we done all of this? Why have we done all of this? Recall, what was our original goal? Our original goal was to define BCH code not as a restriction of Reed-Solomon code, but by some constraints. Say something is in a member of BCH code if it satisfies certain constraints. This was done to say Reed-Solomon itself, we are going to define it in terms of constraints. Reed-Solomon, so what's the, so we're saying Reed-Solomon F star K. All I'm claiming is this is the following. I'm claiming C1, C2, CQ minus 1 belongs to Reed-Solomon F star K if and only if it's orthogonal to the right set of constraints. What is it? It's exactly this object. That is, if and only if you have this property. So this is C0, C1, C2, once we have to CQ minus 1. Here, what should I put? I should put the evaluation points. So this is F star. And here I should put the monomials. From which monomials? From 1 to n minus k. So I have first alpha 1. I'm going to take the first monomial alpha 2 all the way to alpha 2 minus 1. Then I'm going to take the second monomial alpha 1 squared, alpha 2 squared. So this is alpha 1. This will be n minus k. Once again, we got n itself 2 minus k. So this is the parity check representation of it. So some string, some n minus 1, this is exactly CQ, or they can write this as Cn. Is a member of the Reed-Solomon code if and only if this constraint is satisfied. That's the definition of the parity check matrix, and we came up with this. Now, it should be evident that if I want to do BCH, what I want is instead of putting field elements here, I'm just going to put bits over here and ask when can I put B1, B2, Bn such that this combination is 0. That's exactly what we are asking. So BCH is exactly what are those B1 to Bn such that this matrix times B1 to Bn. Notice the multiplication is happening over the large field. Though this vector is a GF2 vector, the matrix vector multiplication is happening over the large field, should still be the all zeros entry. That is the definition of BCH. Huh?
So this you want to say Q.
CQ minus 1, because this is, we are working over S star. Therefore, the number of evaluation points is Q minus 1. So N is Q minus 1. So N is here. Then we have all of this. Is that okay? So BCH, now we have, why did we do all of this process? BCH, we have represented it as a set of constraints. So a particular B1 to Bn is a member of the BCH code is B1 to Bn into that row is 0, the inner product. B1 to Bn into the second row is 0. B1 to Bn into each of these n minus k rows is 0. And what is n minus k? This is exactly n minus k was chosen to be 2t, if you recall. So this is exactly, that is, in other words, B1, B2, Bn belongs to BCH n t plus 1 if and only if for all 1 less than or equal to j less than or equal to b, we have summation bi alpha I to the power j is equal to 1. That's the linear constraint. Now, how many such constraints are there? There are no. What's the number of constraints?
It's 2D.
2t constraints. But is this a single constraint or what?
The coefficient is.
So this is one way to think of it is there are 2t constraints. Each constraint will reduce the dimension by 1. But this is not a constraint. It's not a thing. This constraint is actually checking. Actually, you have to. This constraint is a constraint over a large field. It's not a single constraint. You have to write, when you write say a constraint over, if you're working with BCH, there is no large field. The way you wrote it was from the large field. Finally, it's this one, you have to write all linear constraints, everything in the base field. This is not, one such constraint here is actually R equation, if you recall. This is a, when you write this down, this is an R bit vector, and you're saying each of the R guys have to be 0. So in some sense, each constraint is actually R constraints. Therefore, it's 2TR constraints totally. And that's why I said it's easy to see that it is 2TR. So each constraint is R constraints. There are 2T constraints. Therefore, their BCH code is defined by 2TR constraints. Therefore, it's just the dimension minus 2TR. Okay. But I want to actually, so let's, at this point, we already got 2TR, but I want to be a little more pedantic and say what I want to exactly write, what are the R constraints? What are the 2T R constraints that this is expanding out to? And here is where we will use the fact. So you notice that this is where we will use this map going from Z to trace eta 1Z, trace eta 2Z. There's a reason why I'm going to write it in a column fashion. Eta RZ, where eta 1, eta 2, eta R are linearly or F2 linear. So let's call this map C. Okay. So we had done this before. That is, there's this map going from the large field to the small field as an R bit vector. So stating that that is 0. So trace of summation bi alpha ij I going from 1 to n is 0 is the same as stating trace of, let's call this quantity from for now a. Same trace of eta a is 0. Sorry.
That is eta 1.
right? Sorry, why did I put a trace here? There's no trace here. Check if this is 0. That's what we need to check. After this is 0 is the same as checking this is 0. So let's take one such condition. So I want to claim that this one equation has become R equations. So let's look at one such equation. So let's look at, say, trace of eta k summation I going from 1 to n bi alpha I to the power j equals 0. Now, I want to say linearity of trace will tell me that I can get the summation bi outside. This is the same as summation bi trace eta k alpha I power j equals 0. Now, this looks like an honest to God Boolean constraint. Because this is bi's, these are all elements from GF2. Therefore, this is a honest to God regular GF2 constraint. This was not. This object, this guy is. So all I'm claiming is this guy. This guy is a loaded term. It's a linear equation in the large field. But when you're talking about BCH, you're right. I'm asking how many constraints. I'd write each constraint in the GF2 constraints. So this whole trace business was just to translate that one constraint over the large field back into the small field. So the claim is one of these, so it translates to R such constraints where the constraint looks like this. Okay, fair enough. So what's happened over here on the hand, if you look at it, this one. So previously there was this B1, B2, Bn. You needed to be 0. Previously, what I had put over here in this matrix was this matrix. Now, what I want to claim is each alpha 1 itself expands out into R, guys, and it basically expands out into this, which is basically, if you notice it, this is just phi of alpha 1, that column vector, phi of alpha 2, phi of alpha n, phi alpha 1 square, phi of alpha 2 square, phi of alpha 1 to the power, what is this, 2t. So each phi itself is an R bit vector. So the reason I wrote it as column vectors was so show this. So now this is actually, if you look at it, this is actually a, how many are there? There are 2 TR vectors over here. There are n over here. Okay. So now it's certainly clear that the dimension of BCH n t plus 1, t is at least n minus 2tr. But we had promised something more. I said I can shave off this 2 also. Okay, so why can I shave? So is this fine so far? Is it fine? Everything fine? It's not magic I have done over here. It's all what we've done.
Analysis we did here is given only.
Huh?
The analysis we did here. This is given only. We have
It's if and only if. It's an only if. So yeah. So this is true if and only if this B1, B2, Bn is in BCH NP. That was the definition of BCH NP because we saw that. Because of this, that's the definition of Reed-Solomon. Therefore, which are the BCH codes? You just replace B1 to Cn by bits, and you're asking which are the bits that satisfy this condition. So this was and all of this going to trace and all was just to get the linear constraints to be constraints in the base field, not constraints over the large field.
So you're saying half of these equations are linearly dependent.
The half of these equations dependent. So let's actually look at the what are the constraints? So the constraints are basically these constraints: bi alpha I to the power j, I going from 1 to n. Of course, there were trace of this and all, but I'm looking back in is 0 for 1 less than or equal to j less than or equal to 2t. So let's look at, so the constraints are of this type. Let's consider summation bi alpha I to the power say from L. That constraint I going from 1 to n, and the constraint bi alpha I to the power 2L, I going from 1 to n. Let's look at these two constraints. There are two such constraints going from 1 to 2t. Let's look at these two type of constraints. What is this in terms of this? It's a square of that constraint. So this constraint is trivially satisfied if this constraint is satisfied. Because bi, this is true only because bi's are 0, 1. If bi's were from the, this is not true in the Reed-Solomon world. In the Reed-Solomon world, this constraint is not satisfied if this constraint is satisfied, because there the bi's are actually large field elements. So in that case, the square of this is not this. It's because of BCH, the square of this is this. Summation bi alpha I to the power 2L is equal to summation bi alpha I to the power L whole square, since the bi's belong to 0. Therefore, you can drop off all the even constraints or all the things. So this j going from 1 to 2t, you can only look at j being 1, 3, 5, 7, all the way up to 2t minus 1. You don't have to write down the even ones, because all the even ones are implied by the guys below. Therefore, the defining, that is, the defining constraints for BCH NP are summation bi alpha I power j, I going from 1 to n, only j being j in 1, 3, 5, all the way up to 2t minus 1. There are t of them, each of them, when you go to the base field, they are r, therefore there are tr constraints. That's the end of the story. These constraints are large field. So hence, let's write it down. Hence, parity check matrix for BCH NP is a parity check matrix is the following. As before, we have FQ star sitting here. And here we have odd monomials 1, 3, 5, all the way up to 2t minus 1. And we put in phi of alpha 1, we have to phi of alpha n, phi of alpha 1 cube, phi of alpha n cube, alpha 1 to the power 2t minus 1. So this is a parity check matrix. This is a, so in some sense, this is a TR times n parity check matrix, and hence that's a parity check matrix. Hence, the size of BCH in T is at least and the dimension over G of 2 of BCH in T is at least n minus PR. You save a factor 2, and that's important. You see, it's like a trivial factor. The n is so large, whether it's TR or 2TR, it shows you how close you're coming to the Hamming bound. And actually, if you now stare at this, I want to say it should be now clear why this is the t equals 1 case is the Hamming bound. T equals 1 case, you have only this first one. It goes up to t equals 1. So you only have that. So you have phi of alpha 1, phi of alpha 2, phi of alpha n. You have all possible 2 power r minus 1 elements. You put down all their, what was the parity check matrix for the Hamming code? It was take all the 2 power r minus 1 strings and write their binary representation. And that's exactly what's happening here. Take alpha 1 to alpha n, write their representation this way. You notice that these will exactly be all the distinct binaries. So this parity check is the same parity check we got for the Hamming code for T. And this sort of generalizes it for larger T. Good. So if you recall, a couple of days ago, I had asked Gilbert-Wasserman versus Hamming bound. This is Pavel's question, whether you're doing better than Gilbert. Which one is right? The Hamming bound is right or Gilbert-Wasserman? We do not know in any region. So we could ask the question even on the two extremes. So at one extreme, we had n minus 2 delta log 1 over delta was what the Gilbert-Wasserman will give you. What Hamming bound will give you is n minus delta log 1 over delta. So this is actually a code which does what the Hamming bound does and not what. So it's a code which beats the Gilbert-Wasserman bound for the switching. So your question which you asked, exactly, it's at the corner point, but even at the corner point, it beats the greedy construction. Much longer than what it should. Anyway, is this clear?
Phi is the method of trace of theta 1 alpha.
Yeah. Phi is just you expand this alpha. So alpha 1 was an element in the large field. What you can put only is GF2. So write the RRE representation. Phi, technically speaking, phi need not have been traced. It could be any.
I could have chosen any F2 or F2 basis or F2R and.
Yeah, but the point what was the trace thing which I described was whichever thing you look, it is for some choice of eta 1 to eta r. There is, you could have done anything, but that is actually some eta 1 to eta r is sitting over there. Therefore, this is the underlying. Okay, the reason I wanted trace is to come the next one. Will come. So phi could have been any isomorphism going from the large field as a field to the vector space F2R. You write that and you'll get this. And you get this 2PR cross n. That's the parity check for the matrix for the BCH code. The BCH code is an amazing code which beats the Gilbert-Wasserman bound. It has very good rate. Distance is only constant distance. It's not a fraction distance. Fractionally, it's a very bad. It's like Hamming code. It has only distance. Hamming code at distance 3. So if you look at it over large n, the distance is going to 0. Similarly, because P here, all of this P is, though I stated it, T is true, this is only true for small t. Everything I said is true for all t, but when I'm comparing it to the Hamming bound, there I needed t to be a small t. Because I'm comparing n plus 1 to the power t to volume 2 nt. This comparison is a fair comparison. They are more or less, these quantities are more or less the same only when t is small. When t becomes like omega n, these are no longer the same quantity.
For T equals to theta, only constant distance and constant rate.
Huh? But no, the dimension just kills you off, no? So you want to say T being, so R is already, by the way, R is already something like log n. So T can never be more than n over log n. In this definition, the way we are doing it. Okay. That's the end of the proof. Okay. So one thing which I wanted to now do is I wanted to also talk about, you'll commonly find in literature, given that we done so much literature, you'll find something called the Dual-BCH code, which is exactly what it means. It's the dual of this code. So what is the Dual-BCH code? Why do I want to take it? So the next 5 minutes or so, we'll talk about the Dual-BCH code. Couple of things I need to fix this one. So notice Reed-Solomon code, when we define Reed-Solomon code, I said the set of evaluation points could be an arbitrary set. Historically, it was defined to be only SQ star because that's the case when it is cyclic. But then you move to an arbitrary set and did things you could work that way. And now the name Reed-Solomon actually, at least in our course and in most CS courses, when we use Reed-Solomon, we use it for an arbitrary set of evaluation points. But BCH, the evaluation point is SQ star, the way I have said this. You could have done all this for an arbitrary set also. Same thing BCH, you could have said, I'll just take those polynomials which on this set of points evaluate to Boolean points. You could have done that. And BCH doesn't have to be GF2, it could have been GFP and GFP to the R. You could have done. So all of these are valid things to do. You can also call them BCH. For some reason, the word BCH refers to only this code. You can call them also generalized BCH or something. You can use them BCH. Only thing the things to change will be you'll have to use the corresponding trace maps, and you'll have to look at the corresponding dual functions. The dual this ones. Right now we looked at the dual for when the set of evaluation for Reed-Solomon was F star. If it was an arbitrary set, yes, you'll have to understand what the dual this one is and take that dual and do this whole operation. And notice the dual was very important over here because we noticed that the duals were actually polynomials. One polynomial and there was a square of the polynomial, and because the square was there, we could drop it. If I had chosen another basis in which one was not a square, I wouldn't have been able to drop it off. So here we just observed that so many constraints are actually linearly dependent constraints. We knocked it off. This is under this representation. If you write a different one, it might not be so obvious to write it. So you can do all of that, and those are also called BCH codes, but it's actually I do not know any place where it's actually those are also called BCH, but you can call them BCH codes. Just like Reed-Solomon, now we use it as a generic name for any set of evaluation. Call them. But in particular in literature, when they mean BCH, they almost always mean this. No? Very few times they might go from BCH on F star to F also. I think, for example, the book does this. The book has a BCH, I think it has it only in a problem set. The book, Guruswami Rudrasudan, has BCH code only as part of a problem, some of the exercises. And there it does this. I think in one location it assumes the evaluation is F. The other location assumes is F star. It mixes this. Yeah. Let's go to dual BCH. So dual BCH, as the name suggests, is just this object. Dual BCH parameterized by NT is exactly BCH NT. The dual.
So here we are looking at BCH as subspace of F2 or a
F2. So BCH is only F2. It's just that it has this alternate way of looking at it as a intersection coming from Reed-Solomon. But once we have it, we forget the fact that there is an higher field out there.
It's a subspace of
It's a subspace of F2 power n, where n is F2, where n is 2 power r minus 1. Okay, so this is just one. So what is this guy? So by definition, we know that if BCH is being defined by a parity check matrix, the columns, the rows of this parity check matrix are essentially the elements of the dual code.
Just one question. So if suppose I have F2,
yeah,
and I have F2 power R1 and F2 power R2, both extensions of F2.
Yeah.
And I define and they have same degree parameter for both of them.
Yes.
Two Reed-Solomon codes, one for F2 power 2 power R1 and one for F2 power 2 power R2.
Yeah.
And take the intersection in F2 power 2 power R. How do I know that this BCH code say it will always?
Notice the evaluation points are different. No, the one it's 2 power R1 minus 1, the other is 2 power R2 minus 1. So what you are now stating is I will only evaluate it as both of them on this multiplicative side. It's then does it have
the same?
Then you happen to get the same BCH. That's what that's right. Yeah. Okay, so already we have seen this object. What is the dual of BCH code? We have defined BCH code by a parity check. So if you define it by a parity check, that means every row of the parity check is essentially a member of the dual BCH. And furthermore, the span of those rows is the dual BCH. The dual BCH is basically a span of all the rows of any element in the span of the rows is a member of the dual BCH. So what I want to say is there's a nicer way of writing that span. So Mon-Wed by construction. Dual-BCH. This span of rows of, not by construction, by this was just by definition. Span of rows of parity check matrix of BCH. Why? So in that sense we understand it, but let's look at what does the span look like. What does the span look like? For the span, actually let me not go to the 2t minus 1, let's go to the 2t when we put it. We are just throwing, when you're taking the span, it doesn't matter if I put dependent rows. So let's put them in. So what does the span look like? How does the span look like? So it's some linear combination. So every row I have to decide whether to take the row or not the row, and then take some. Basically, it's a GF2 linear combination. So I decide to take some collection of rows and some collection of rows I don't take. Sum it up. That's the span. So the span looks like this. It's basically summation. So I want to say P, J, and K. J going to K going from 1 to R. It tells you J going from 1 to 2T. Trace of J. What does an arbitrary row? I will take a linear combination of the two TR rows. So each row I have to decide whether to put it in or not, and that's basically this number BJK. It's telling you whether BJK is telling you, so there are two TR possible rows, and I'm telling you whether I'm putting it in or not. So where the BJKs are in 0, 1. So any element in the span looks like this. Okay, that's the element of the span. And the alpha is this. What is alpha? Alpha is a generic name for which, depending on which column you are. If it's alpha 1, if it's a first column, I put alpha 1. If it's second column, I put alpha 2, so on. So it's just the evaluation of this function on all points, all the f star points. Now once again I can do linearity. So this is the same as J going from 1 to 2T, trace of BJK, eta k, taken from 1 to R, BJK, eta k. Is that right? Yes. Now, eta k are linearly independent elements. So if I take choice of BJK, this just goes over any possible beta 1, beta 2. This can be any number in the large V, any element in the large V. So instead of these guys, I could have made this look like J equals 1 to 2T, trace. This is beta J, alpha J. Then beta J is some element in the large field. As I range BJK over 0, 1, this is just going to range over all elements in the large field. It's just going to be this object. And then what is this? This is just, now once again I'm going to take trace inside. So it's trace beta J, alpha J, J going from 1 to 2. So what does this, the Dual-BCH? It just looks like, take a function, take a low degree function, take a degree 2t function with this one. It's almost like Reed-Solomon. Take it, but don't put its evaluation evaluate it and then take its trace and put it down. That's all. So all I'm claiming is, so hence, dual BCH NT is evaluations of trace of degree less than or equal to 2t. But notice it's not degree, it is without a constant term. I can't have the constant. That's because I didn't have the constant term. Degree less than or equal to 2t without constant term. Polynomials in the bunch. So this is an equal way of writing dual BCH. Dual BCH is just it's like Reed Solomon was the evaluation of arbitrary polynomials of a fixed degree. Dual BCH is evaluations of not arbitrary polynomials, but the trace of arbitrary polynomials over F star. And because we are working with F star, you have to drop the constant term. If the whole BCH exercise I had done it with not F star but F, then it would have been a honest to God, you would have actually had, you could have included the constant term also. Okay, so this is dual BCH. The thing about dual BCH which we will not prove, and notice what's the size of dual BCH?
At most 1 plus p.
Huh?
At most p.
It's at most PR. Huh? For small t's, that's what we will show that these are actually linear independent, so it will be exactly PR. So what is known as, so the size of dual BCH NT is 2 power PR is less than or equal to 2 power PR. These are things which I will not prove, equal to 2 PR with equality for small t. So this is roughly like n plus 1 to the power n. So you have so many code words in the BCH code, in the dual BCH code. This is something I will not do. No. That's the size. What about the distance of dual BCH? This happens. The distance of a code in dual, we haven't seen any theorem which connects this one. You can ask what's the distance. This is a non-trivial theorem. These are called the Weyl bounds, and follows that from the Weyl bounds that the distance of dual BCH NT is actually greater than half minus the fractional distance t by square root. The distance very close to half, they almost meet the Plotkin bound.
This we can get from looking at the minimum number of independent columns. in
You
the
can,
BCH.
but it's
But that's
that
not
no,
easy.
that's not easy to do. This is, I don't know of an easy proof of this theorem at all. Even since I can spend a whole lecture on this proof, but it requires a fair amount of math to do this.
So that's from that these are projections of Reed Solomon codes.
So yeah, no, I don't. You don't get any. I don't see how to get anything easy out of this. So beyond forward. So once again, I want to say, BCH we saw beat the Gilbert-Verschomo. They were at the Hamming. They were at the Hamming. This one, not at the Gilbert-Verschomo. This one at the BCH was happening at in the curve. Delta. So delta equals half. is R, R, one, and this was the GB bound. Okay, Hamming bound was that. And both BCH Hamming are all sitting over here. They have rates very close to 1. And notice that if you recall from last time, we had said that if you're looking at delta going to 0, you're going delta going to 0. The Gilbert-Wasserman says there exists a code C so that the rate of the code is greater than or equal to 1 minus I think delta 1 minus 2 delta log 1 over delta. That was what GB said. The Hamming bound tells you that rate should be less than or equal to 1 minus delta log 1 over delta. And what we had shown was actually the BCH is sitting here. So you beat the Hamming bound. You can ask now the dual BCH is going to sit here. It's going to be over here. The dual BCH is over here. So delta going to half minus delta going to half. That is so that delta being equal to half minus epsilon and epsilon going to 0. We are looking at things over here. So GB will tell you, if you recall, what did GB tell you? GB will tell you that R is, there exists a code C with R being omega epsilon square. And then the Plotkin and the Elias-Basiligo had said, Plotkin versus Elias-Basiligo had given us that the rate is order epsilon. And we have one. And if you look carefully, this one, they're not at the Plotkin bound, but what the dual BCH achieves, if you look at it. So you can ask if number of code words, if number of code words is n to the power p. If you have n to the power p code words, what's the distance you can get? What's the distance you can get? Gilbert-Wasserman, the greedy will give you, greedy or probabilistic. Gilbert-Wasserman will give you that the distance will be greater than or equal to half minus square root t log n by n. That's when the epsilon square and things all match up. But what dual BCH gets, it gives you t over square root n. So it is t over square root n is better than this one. So Gilbert dual BCH actually outperform both dual BCH and BCH outperform Gilbert-Wasserman at their respective ends. Dual BCH we have already seen it, fully analyzed it. Dual BCH it depends on Wales bounds, which I don't know how to, which will be on the scope of this. I can put it as one of the projects if one of you is willing to present it. So Swastik has nice lecture notes for Wales bounds. We can discuss that as one of the. So yeah.
The definition of BCH codes is given n equals 2 for r minus 1.
Yeah.
So you take a degree r extension of f2.
Yeah.
And for over there, you can reach some codes which intersect the base field coordinate, right?
Or sorry, can you
So
repeat?
you're given n equals 2 for r minus 1.
Yes.
So you take a degree r extension of the base field.
Yes.
You take an external code over there.
Yes.
And intersect with f2 power n. Right?
Yes.
My question is, if you have two different field extensions, they will be isomorphic. But let's say you have two different field extensions
Yes.
of the same degree, and
Yeah.
you take
But
a
you're changing the set. So for one field, so the set of evaluation points is just the, so previously in all of this, we always evaluated it with the evaluation points being the
whole field
the multiplicative group of the field. So if you're having two different field extensions
of the same degree.
of the same degree, but if you choose, but the point is now the codes are there, what's the evaluation point, sir?
So both of them are evaluated the multiplicative.
Multiplicative group of the smaller field is what you're doing. Because otherwise, the block lengths of the two BCH codes.
So same, I'm getting two different field extensions of same degree.
Yeah. So what you're doing is the
Yes, I'm getting two different irreducible polynomials of degree r. And I take f2x by ideal of fx and f2x by
So there is R and then there's capital R, which is R times some say S, because, and then you're looking at two fields, F2 to the R and F2 to the.
No. I'm looking at two different instantiations of f.
Yeah, but if you have to compare them, you have to come. So if you want to have them to talk about them, one should be a subfield of the other. You cannot talk of them otherwise.
You're
No.
talking about the same set F2 to the R, but the
In
way
two
you construct
different
it is using two different derivatives. You're saying what happens when you.
Oh yeah, they will all. It doesn't matter. None of this really matter on which derivatives. So then I didn't follow your question.
Okay.
Repeat the question again.
Suppose
Actually, let's stop
Okay.
this one and.
I'm saying suppose